So guys, welcome back. So as I was saying now is that multiplying by the reflection matrix in the x-axis, because it's similar to the unit matrix. And as you know, if you multiply a matrix by the unit matrix, you get back the same members or the same matrix. But in this case, because they have a negative sign with one of the ones, then the row where that one is negative, the row in the result is going to be all negative in that row. Everybody is clear on that? Raise your hand, let me see it. Guys, if you don't respond, I don't know whether or not they're clear. Miss Cabrera, are you clear?
No.
Say that again, Miss Cabrera.
No, sir.
Okay. Miss Green, are you clear?
Yes, sir.
Just want to stop.
Okay, so this is what I'm saying. This is a reflection matrix. This is a reflection matrix, right? What are you doing with this reflection matrix? You're using it to multiply this matrix, right? Are you clear on that, Ms. Green and Ms. Cabrera?
Yes.
Right. But we are saying that when you multiply these two together, this is what you get. Are you clear on that? Are you clear on that?
Yes.
Right. So I'm saying the regular way how we would multiply two matrices, row by column. You don't have to hurt up your head about that. That's all I'm saying. All you need to pay attention to when you're multiplying by these transformation matrices, you just pay attention to the row where you have the negative values in, right? So what that means then? All right, so we are multiplying by this transformation matrix. You look at the ones. We don't have negative zeros. Only the ones can be negative, right? Which row of this matrix would be the one negative? The top row or the row below?
The row.
The row below. So the effect of this negative one in the row below mean that when you multiply this matrix, these numbers that are in the same row below, that means the 4, the 3, and the 3 here, all you're going to do is to add a negative sign to them. -4, -3, -3, and you get the answer. That's it. You follow?
Yes.
Is that clear now to you, Miss Green? Miss Green?
Yes, sir.
Right. I know you're tired, Miss Green, but you have to try keep up and pay attention. All right. So all I'm saying, it is easy to multiply by these matrices because the matrices don't really change the numbers. All it does is change the signs. And you can change the sign based on the row that you have the negative in. So if the row below have a -1, then you change the sign of the row in the pre-image. You change them to all negative. Suppose now the -1 was up here. What would you do? Miss Cabrera.
Sir, repeat.
If instead of having the -1 below and you have it above, what would you do in terms of your multiplication?
Sir, all the numbers at the top, I would put a negative sign in front of it.
Exactly. Is that clear to you, Ms. Green? Miss Green, work with me, please.
Sir.
Is that clear that if the -1 is in the top row, what you would just do is change the sign of the numbers in the top row in the pre-image? Is that clear?
Yes, sir.
Okay, good. So I'm just giving you the easiest way how to work with these numbers, because when you're in exam, you're not going to remember the whole process of row by column when you can just change the signs. You want to make your life easier. You don't want to work harder. You want to work smarter. All right. So that is for that first example. Look at this example now. Find the reflection of triangle ABC with vertices 1, 4, 1, 3, and so it's the same vertices, but this time they wanted to have a reflection in the y-axis. Now, what I want you to do the calculation quickly for me. You should know the reflection matrix in the y-axis. You should know how to write these in column form. So write these in column form, pre-multiply by the reflection matrix, and give me the result of your image. So do that for me right now. Quickly, you have about 2 minutes to do that. Raise your hand when you're finished, guys. All right, guys. So can you just tell me what your image A-B- will be?
Sir, my answer is going across.
Yes.
-1, -1, -4, and then below we have
Hold on this way, son. Hold on. So in the top row, what you have? All right, let me write the pre-image here too. So you have A, B, C. You would have 1, 4. You would have 1, 3. You would have 4, 3. What's the reflection matrix here now, guys?
-1, 0, 0, 1, sir.
All right, so it would be -1, 0, 0, +1. All right, so when you do the transformation now, remember that these numbers going to come back in the same order, so you can basically write them back over here. All right, so what you do now next? What you notice that there's a -1 up here. So how will that affect the multiplication process?
All the
Everything is up.
numbers.
So all the top row image going all be negative. All right, guys, everybody got that? Raise your hand if you get it. Miss Green, did you get that?
Yes, sir.
Okay. Miss Dorothy? Ms. Dorothy, is Ms. Dorothy there? Maybe not. All right, you may lower your hand now, Ms. Wilson. All right, so that's the idea behind it, guys. So pretty much using these transformation matrices are done in the same way. So the first thing you want to do is write your coordinates in column form and so on. Now this part you need to know though. Suppose you have multiplied this. Now you want to put back these images on the graph. You have to now write back these in coordinate form. How would you write back your image in coordinate form? What would you have for A? A would be what? A dash would be what? What would be the coordinates? Come guys, Miss Ways.
Sir, next 1 and 4.
-1 and 4, sir.
You have -1 and 4.
And 4.
This means is X going to be -1, Y going to be 4. What's B dash?
-1 and 3, sir.
So that will be -1 and 3. And P dash?
Negative 3.
-4 and
-4 and 3. All right, so you all have the understanding of what you're doing now. So it means that any of these reflection matrices you are carrying out to multiply your pre-image is the same process that we did here that you're going to follow. You write your coordinates in column form in one big matrix for all of the coordinates. You find your reflection matrix or your rotation matrix. You pre-multiply your pre-image by that matrix, and then you get the image. Now let us look though, because these two matrices have the ones coming down the diagonal like that. Let us see what effect the other matrix, where the ones going across where the zeros are. Let us see how those matrices would affect your transformation or your image, all right? So let us look now. This now was the one that we just did. And so here we pre-multiply by that, then this is what we would have. All right, next here is example 3, guys. Now, it says find the reflection of the triangle ABC in the x-axis. No, well, I think there's an error right here. So correction, this should not be in the x-axis. So it should be in the line y equal x. All right. So that's an error. I'll try to make that correction. All right. All right. So with that said, now, what are we going to do in this process, guys? Anybody?
So yeah,
Go ahead, Ms. Cabrera.
yeah, go right to the image for y equal x first.
No, not the image, the pre-image. So what's a pre-image? You're going to write these in column.
0.
All right. And what next you do after that, Ms. Cabrera?
You write all the points for A, B, and C in vector form.
All right, but so which matrix you're going to write now? What you're going to use to multiply them? What's a matrix?
0, 1, 0, -1.
0, 1, 1, 0. What is it? Go again. Apparently, I'm not following you well.
0, 1, and then 0, and then -1.
You sure that is the matrix? What is the matrix, Miss Green? Reflection in the line y equal x. What is the matrix?
0, -1, -1, 0.
Miss Wilson, what is the matrix? I see how easy you forget the matrices because you don't.
0, 1, 1, 0.
0, 1, 1, 0. That's the matrix. All right, so first we write the pre-image in the column form. Then we write the matrix that we're going to use to multiply it. So this would be the matrix. So this is a matrix that multiply to give a reflection in the line y equal x, guys. Don't forget it. So in the line y equal x, these ones are positive. There's no negative in them. Is that clear, Miss Cabrera and Miss Green?
Yes, sir.
Yes, sir.
All right, so now that we know which matrix we are multiplying by, then we are going to pre-multiply the pre-image. Now, before I put in the results, just guess and tell me what the image value is going to look like. Give me a wild guess. Let me see if you are thinking.
Everything is going to be positive.
Well, yes, you're going to have positive, but you don't think any other changes will happen? All right, let me put in the answer. This is what happens. What you notice happen with your image and when you compare it to the pre-image.
This pitch, like the one that was at the top is now at the bottom, and the one that was at the bottom is now at the top.
Exactly. So this is the effect when you change the ones from the diagonal. If you change those ones to 0, it will interchange the x and y values. Everybody see that? So what used to be the y will now become the x, and what was the x now become the y. Is that clear to everyone? Guys? All right, let me highlight that. So this is our pre-image, and this is our reflection in the line y equal x. This is what we're with the transformation matrix we are multiplying by. Because we have zeros along this diagonal instead of ones, what it does to these values when you multiply through, the bottom row of this becomes the top row of the result or of the image. The top row of the image now becomes the bottom row. Sorry, the top row of the pre-image now becomes the bottom. So this is really what happened when you use that matrix. Everybody see that? Is that clear? Guys, raise your hand or say something.
It's clear, sir.
Okay. All right, so now you know the effects of this matrix when zeros run along the diagonal. Then you know that you have some other matrices with zero run along the diagonal. So you should be able to determine the effect that they will have when you multiply by them. All right. So it means then, if these, and remember now guys, once you multiply these out, you have to write back your A dash B dash in coordinate form if you're putting it on a graph. And even just to give back the results, you have to give back the results in coordinate forms, not in the vector form. These are in vector form, or column forms. All right, so let us see if we can look at another one. So here we have, all right, I guess. All right, tell me guys, before we get to this matrix, what do you think would happen if we're trying to find a reflection in the line y equal minus x? What do you think would happen?
So I think the positions would switch like we're switching this, and then the
Tell me the matrix for reflection in the line y equal minus x.
I feel like it would change like how it changed for this
The
side.
the ones would be what?
The ones would be negative, so I guess all the answers would be negative.
The ones would be negative. So it means all of these going to be negative. That is if you're reflecting in the line y equal minus x. All right, let me ask you some others, right? So that you get the general idea. Suppose I say a rotation of 90 degrees. What would happen? Which one are the matrix that you would be using for a rotation of 90 degrees?
0, 1, minus 1, 0.
Is that the one that rotates for 90 degrees?
Yes, sir, I think so.
All right, let me check it and make sure, because I don't want to tell in a lie. All right, so back to the rotation matrix. This is the one, rotation 90 degrees, right? So you see what it is? It's a -1 above. And the diagonals are 0. Everybody see that? So this is a rotation for 90. This is a rotation for 270. These two are similar with the 0 diagonals. But the -1 above would be for 90. The -1 below would be for 270. Now, for 180, these look exactly like the unit matrix. So the ones for the rotation of 180, you write the unit matrix and write the ones as -1s, right? And for the rotation of 360, you just use the unit matrix by itself without doing any changes to it. All right, so going back now to what we were saying down here. So we're looking at this one. All right, so here now, I am asking you, suppose we are, all right, so let me put back this. Suppose we are doing a rotation of 90 degrees. What would be the transformation matrix? Come guys, they just look at them a while ago. Yeah.
Repeat.
A rotation of 90 degrees. What is the transformation matrix?
0, minus 1, 0, 1, 0, sir.
So it means that this will be a -1. Now, if I by this matrix with a -1 up here, what do you think will happen? What's the value you're going to get? These going to be
The value is going to be negative, sir.
These going to interchange the same way, but what?
That value is negative.
All right, let us check. So 0 times 1, 0, negative,
0.
negative 1 times 4, negative 4. So it means that this value up here going to change to negative. So all the values above going to change to negative. So it's going to flip, and because the 1 is above, it means all the values above in your image, after you flip it, going to become negative. All right, guys. Now, it goes to say then, if you were rotating 270 degrees, and that is a negative 1, what do you think would happen? Come, guys.
Sir, the bottom values them go to negative.
So you would have the flip. And then now the one that below now going to be negative. And if you want to check, you just multiply it out. So you'd have 0 times 1. Remember, you multiply row by column, right? So 0 times 1, 0. Negative 1 times 4 would be 4, right? So what it means that this top value going to be positive 4. Then you know 0 times 1, 0, 1 times 3, 3. So this is going to be positive 3. 0 times 4, 0, 1 times 3, 3. This would be positive 3. Now we use this row. So negative 1 times 1, negative 1. 0 times 4, 0. Negative 1 plus 4 give you negative 1. So it means that all of these values, when you flip them, they become negative. Is that clear, guys? Guys? Guys?
Yes, sir.
All right. All right, I know you're under a little, well, maybe a lot of stress for some of you, but at this point in time, you try to maintain your composure and just relax and absorb as much as you can, all right? All right. Now, with that said, if you are to use any of those matrices, you are taking the same approach. Now, here we have some general, remember we talk about enlargement. We have what I would call an enlargement / reduction matrix. Remember, if you're enlarging, K has to be a number greater than 1. But if you're reducing, K has to be a number between 0 and 1. That means it has to be a fraction. Now, the general enlargement matrix would be this. So if this is the matrix of enlargement or reduction, now, when do you have an enlargement? If this K value is a number greater than 1, when you multiply by this matrix, you will get an enlargement. Your image going to get bigger than what it was. If the K value is a fraction, for instance, a half, when you multiply by this matrix, your image going to reduce. It gets smaller in size. It's going to get half the size of what it was. Is that clear, guys? So for enlargement matrix, this is a general form. So what you need to do is to just remember that the K's run along the diagonal. And so if you're doing an enlargement, you just choose a value for K that you're going to enlarge it. So if your K is, say, 3, then you would replace these two K with 3, and then use the matrix to multiply your coordinates, right? And remember that these two values have to be the same for it to be an enlargement or reduction. You can't have k equals 3 up here and k equal and a different number down here. It won't be an enlargement or reduction matrix until you have done that. These two values have to be exactly the same. So in other words, it has to be what? What kind of matrix it has to be? It has to be a diagonal matrix. Remember diagonal matrix, guy? All right. Now, so this is all that you need to remember for the enlargement matrix. Just put in whatever k value you put in here, use it to multiply your coordinates in the same way, meaning that you're going to have to write your coordinates in column form and so on. Multiply by this matrix, whatever you get to write your image, and you write back your image into coordinates form. All right, so these are what you would have learned from before. If k is greater than 1, then it's an enlargement. If k is between 0 and 1, then you have a reduction. All right. So this is an example of an enlargement matrix. So this is going to give you twice the size of the pre-image. All right. Here, there's an example here. So you would multiply your matrix by your enlargement matrix. And then you would get your image to be twice what? So your image going to be twice, the coordinates going to be 2 times what they were for the pre-image, right? So this is 1, so it becomes 2. This is 1, it becomes 2. This is 4, it becomes 8. This 4 becomes 8. This 3 becomes 6. This 3 becomes 6. So you write back these in the form of coordinates, plot them on a graph, and you should get a bigger image than your pre-image. All right, guys. So an enlargement may be combined with some other transformation. So when you combine some other transformation with an enlargement matrix, you may get something of a different shape than what it would be just by enlargement alone, right? Now, remember we talk about shear or stretches. Now, this is a matrix that give you, remember the shear that we talked about in the previous transformational geometry. This matrix has the same effect. If you multiply your pre-image by this matrix, by putting a value for k, you will stretch it along the x-axis, right? So this would be like the unit matrix, where the k, instead of having 1 up here, you have a value k. So k can be any value that you choose to put there. So if it's a number greater than 1 and you put k, you're going to stretch it along the x-axis, right? If you put k below and the 1 above, it will now stretch it along the y-axis. Now, if you can recall what I was saying when we started, that if you consider these matrices in terms of the top row being x and the bottom row being y, then you will clearly see that when you stretch along the x-axis, it means the k is above in the x row. When you stretch along the y-axis, the k is below in the y row. Is that clear, guys? Is that clear? Raise your hand. Ms. Wilson, is that clear to you?
Not quite, sir. Sir, I don't remember which side it will draw on. For the right side or the left side. So that kind of confuse me.
No, it really doesn't matter which side. The side will be dependent on the sign. So
okay, sir.
If you have a negative value for k, it's going to stretch to the left. You have a positive for k, it's stretched to the right.
Okay, sir.
Direction of stretching is just based on the sign. All right, so other than that, is it clear?
Yes, sir.
Right. So remember now, when you have your X and Y axis, and you do a stretch of some object. So let's say you had a box. And you do a stretch or a shear. When you stretch this object, it will along the x-axis, it's going to have an effect looking something like this.